Right, so this is where we were. We had this log-n lower bound by Mihai and Eric Demain. And so the question is, of course, can we go beyond log-n? And so in 2007, Mihai actually had a technique that could prove these log-n over log-n squared lower bounds, so like almost a quadratic improvement, under some sort of slightly unnatural assumptions about sort of the machine that you're running your data structure on. And so his assumption is that the word size is really large. And so at this time it seems weird that this would get higher lower bounds, but it's actually to make the problem natural that you assume the word size is big. We'll get back to why this limitation is there. So you really wanted this lower bound for log-n bit words, because that's the assumption we normally make. But it only holds if the word size is really large. But his technique is really nice and natural. And it seems closed, right? And so in 2012, yeah. So that's what I was trying to mention. That it's actually okay. Maybe you'll see it in a slide or two. But the problem that he proves the lower bound for only makes sense for really large cell size. So that's the weird thing. It's not. Yeah. So the problem, you prove the lower bound. Maybe I can actually show you what it is. But yes, but then the data structure problem that you're solving doesn't make sense unless the word size is big. That's the thing. You'll see it in a slide or two why. But yes, it's true. That's the intuition. That it seems that you'll also have a lower bound for the smaller case, but then the data structure problem doesn't make sense. Okay. Actually, so in fact, the output size in this data structure problem will be these log to the 2 plus epsilon n bits, the answer to a query. And that's why it makes sense that the word size is at least this big. Otherwise, it takes a lot of time just to write the output. So that's the intuition. Okay, and so in 2012, I managed to get it down to actually log-n bit word size, and then the lower bound holds. So this is the two steps. We'll start by Mihai's approach, and this last one is sort of like a refinement of his idea, you could say. Okay, so the problem we'll be looking at now, where we can actually prove this log-n or log-n squared lower bound, is like a generalization of this prefix sum problem. So if we go to 2D, now we have points with weights in 2D. So they all have an integer weight. And then a query is a point, and you want to sum everything in this bottom left corner. Okay. So this is like a sort of natural data structure problem. It occurs a lot in databases where you're doing something, some values for things that are, let's say, maybe each of these could be employees again, or cars maybe, and you want to. This is maybe the mileage of the car. This is the price of the car, and you want to know some values for cars that cost less than 100,000 and that have driven less than 100k kilometers, whatever. So this is sort of a natural problem, and so the answer to this query here is 9, because you sum these weights inside the rectangle. And just to make sure the problem is clear, the answer here is 12. You sum the weights. And again, the answer is 12 here. Okay. And so an update consists of, let's say, insert a point with the weight. Okay. So it's just a generalization to 2D of this prefix sum problem. And so Petrascus' approach was, again, like the chronogram approach, you consider a sequence of n updates ordered by time. You divide them into these epochs again, like in the chronogram technique. Okay, so the smallest epochs are closest to the time of the query. The query is at the very end, and they grow exponentially in size as you go backwards. And sort of the intuition is, right, so Mikkel and Mihai had this technique for proving log-n over log-n static lower bounds. Right? So the idea here is you want to prove a static lower bound per epoch. So instead of saying you want to read one cell for each epoch, you want to read essentially log-n over log SW over n cells per epoch. These were the lower bounds we could prove before, right? Maybe this was a T in some cases, maybe it's a W. And the observation is, if you remember from the very beginning, if you have TU time and you're processing n updates, you can only change NTU cells. So essentially this space in here becomes NTU, and you divide by n, so it's like TU. So you're getting something like this. If you could prove a static lower bound for each of these epochs, then you would get then you can sum them up over all the epochs and you get a squared lower bound, right? You get log n over log w to u per epoch, and there's log n over log w to u of these epochs, and you sum them all up and you get this lower bound. So that's this idea, right? You want to prove the static lower bound on each of these epochs. Sort of the intuition. So then we want to prove it for a concrete epoch j, right? So if you remember the Mihails and Michels static lower bounds were proved by this communication complexity approach, right? Where one of the players had a bunch of queries and the other player had the input, right? As we saw in the beginning. And so the setup here, if we want to prove that you need to read a lot from epoch j, so the intuition is you would give Alice a bunch of queries, like slightly fewer than the number of updates to the epoch. Remember, we had set it like a few log factors smaller for Bob's communication to stay small enough. And Bob holds the updates of epoch j. This will sort of be the natural approach to take. And then what we want to do is we want to say, if I had an efficient data structure that didn't read too much from this epoch, let's say, then I want the amount of communication in this protocol that I can derive to be small, right? That's basically the intuition. I want the communication of the protocol to be proportional to the number of memory reads that is happening to what was written in epoch j. Right? So that's what I want to do. I want to make a reduction from the data structure to this protocol where the communication is proportional to the probes to epoch j. Okay? So in some way, I don't want to communicate when the data structure is reading outside epoch j, only when it's reading things that are colored with this epoch j. Okay, that's the intuition. Okay, and so essentially to make this work, we're just going to say that basically Bob will know all the epochs, and Alice will know all the things that happened in the past. And in some sense, if you say that these updates that are happening in these different epochs are independent of each other, the amount of communication that it takes to solve this problem should not change, right? Because if what's going on over here has nothing to do with the red stuff, the communication lower bound should still be the same. If I tell Alice all the black stuff, it shouldn't help. Okay, so that would be the setup, that Alice knows everything that happened in the past, Bob knows all the points. And of course, this static lower bound does not change. So basically, we have a communication lower bound that says something that if Alice has kj queries, she basically needs to send all of it, or Bob needs to send essentially all of his data. Okay. This is just using the communication complexity tools. You can improve a lower bound like this, right, for this problem up here. So it's just essentially like we did for the polynomial evaluation, right? Using rectangle arguments, show that Alice sends all of her queries, and Bob sends almost all of his data. And the reason why it's almost all of it is because of the problem. We can't prove a beta to the j lower bound for this concrete problem. You lose a log factor, log to the epsilon factor, but that's irrelevant here. Basically just saying that essentially Bob has to send everything, or Alice has to send everything in this protocol. Okay. So you can prove this communication lower bound. So now we just need to get an efficient reduction from this data structure to a protocol. Right. And so the idea for the protocol is that, as before, Bob builds this, takes a dynamic data structure and runs all the updates on the data structure all the way to the end. And then the first step is that in the communication protocol that we are designing is that Bob sends everything that's happening in the future, right? All these smaller epochs. And again, if you remember, these are really small, right? It's this little o of beta to the j, because it goes down by this factor beta each time. Like for the chronogram technique, the communication it takes to send all these future epochs is smaller than the lower bound. So we can easily send everything that's happening in the future. All the cells that are being written, Bob can start by sending that to Alice. Okay, so that will be the first step in this communication protocol. And now, so Alice knows everything that's happening before epoch j, right? So she was told everything that happened in the past, okay? But not from epoch j and forward. So what she'll do is she'll start by running all these updates on the data structure, and then she stops just before starting this epoch j. Okay? So she knows what the data structure looked like before processing the updates of epoch j. And Bob has sent everything that was changed in the future epochs. Okay. And now the idea is, as we said before, we want the communication between Alice and Bob to depend on the reads into this epoch J, into the stuff that was written in epoch J. So we don't want Alice to speak when what she's requesting does not belong to epoch J. Okay, that's the whole idea. We want it to only depend on the probes to epoch J, because then we can sum them all up at the end to get a lower bound. Right? We want to prove log n over log n reads per epoch. Okay. So this, I just moved it up. And so how would we try to do this, right? So we're trying to design a protocol. We've done this so far. Bob sent all the future. Alice built the data structure up to just before epoch J. And now they want to answer the queries. Okay, so the first thing to observe is that, so Alice runs the query algorithm. It asks for a cell. And what you can see is if it belongs to some of the small epochs, right, the future, all the small ones, and because Bob sent all these memory cells to Alice, Alice can recognize this because the address is written there, and she knows the content, so she can continue running the query algorithm, right? So if it reads in the future, she doesn't have to speak to Bob. So that's good. So we're happy, so we can continue. So now, the problem is, if it doesn't belong to the future, she can check this, but now she knows it doesn't belong to the future, but the problem is she doesn't know if it belongs to J or any of the past epochs, right? She doesn't know. So it can be either in epoch J or in the past. So this is, and she can't recognize this without asking Bob. And so this gives a problem because then the communication would be proportional to the total number of probes, both to epoch J and all the past epochs. So we need some way of getting around this so she doesn't have to talk to Bob when it belongs to these past epochs. And so Mihai's solution to this problem was Bob will speak a little bit more. So in the beginning, he will also, maybe I need a picture now. So let's draw a picture. So let's say this is your RAM, this is the memory cells. Let's say the green ones are the one that belongs to epoch J. And then you have some orange ones, which are all the ones in the past. Let's say like this, something like this. And now what Bob will do is he will take, so basically he wants to tell Alice what these cells are, right? These green cells, the ones that belong to epoch J. So these are the epoch J cells. Right, so he wants to tell Alice what these cells are, because then she knows, right, if she's, whether it belongs to epoch J or not. And you want to do this sort of without sending too many bits. And okay, so we also know the number of them, right? There's the update time was TU, there's beta to the J updates, so the number of these cells is only beta to the J TU, right? And so the trick here is you can send a Bloom filter, which is a data structure. It's basically a data structure that can answer membership queries, so it can store a set of integers. So Bloom filter here. So you store a set S from some universe U. It has size n. And what guarantees is that on the query X in this universe, if X is an S, it says yes. If X is not an S, it says no with probability 1 minus epsilon. Okay, so it has some false positives. So this is a classic data structure called a Bloom filter, and you can build a Bloom filter for n keys with false positive rate epsilon, taking n log 1 over epsilon bits. Okay. So this is like a classic data structure from the 70s. So basically the idea is that Bob built such a Bloom filter on these memory cells where this epsilon is 1 over polylog. Okay. So a false positive rate of 1 over polylog n, and sends it to Alice.
So the 1 over polylog is, in order to counter, to be something smaller than 1 over TU?
1 over TQ, actually, the number.
TQ, oh,
yes.
the number of the TQ.
Yeah, the total number of queries, yes. Because basically, right, when Alice is running, simulating the query algorithm, she'll ask the Bloom filter, whenever it reads a cell, she'll ask the Bloom filter if it was green or orange, right? And then sometimes when it's orange, the Bloom filter will say it's green, and she'll ask Bob for the contents. But if the false positive rate is small enough, this communication doesn't matter.
So the savings here is between the log n and the log s that you
yes.
save
yeah.
just for the trivial.
Yeah, exactly. Yes. So you send this Bloom filter. Yeah. Yes, they have shared randomness in this case, yeah. Or I think actually you can make a Bloom filter work by saying you can have log squared n random bits that the one player can pick on its own. Right? You have a log n wise independent hash function would suffice, and then so Bob can find a hash function that works, write it down, and send it along with it. Yeah, but you can also have shared randomness. Yeah, it does. Yeah. Okay. Okay, so this is fine, but the problem is that the communication lower bound that we proved was only this beta to the j over log epsilon n. Right? This is the communication lower bound we got out, and this is where the large word size comes in. Because now we just change to a different problem. We just say that the weights on the points have log to the 2 plus epsilon n bits. Okay, so these are really large weights. And then the communication lower bound actually is higher if you prove the communication lower bound. Something went wrong again with the math on this machine.
Oh, that should.
Yeah, the omega goes down. The communication lower bound goes up if you increase the size of these weights. That's why it's sort of an artificial problem, because the weights are really, really big for the lower bound to hold. But that's the idea, right? You just increase the weight size such that this Bloom filter doesn't matter, right? It's less than the communication lower bound. And then you get the lower bound out that you wanted at the end. Because now you can, now exactly what Alice will do is, right, she'll run the query algorithm. If it reads in the future, she knows the content, she can see this. If not, she asks the Bloom filter whether the cell belongs to epoch J or not. And if it says it does, she asks Bob for the contents. And then you also have to be careful, you have to do all these K queries in parallel, do one probe for each of them, check which ones you need to ask for, and then you ask, and then you continue. But that's the idea here, right? So you send this Bloom filter to help Alice not having to talk when it belongs to the past. Okay, right. And of course, the main issue why you can't get down to get low bounds for the case where we really care about like log n bit weights or maybe just 0-1 weights is that you have to somehow, Alice has to know when the cells belong to the epoch J or to the past. And that's the whole problem with the technique. And so if you look at it, if it belonged to the future, it was easy. And if not, she does not know. And Bob has to send the Bloom filter. Right. So let's see what we can do to actually get it down to only requiring log n bit weights. So we have to change this sort of reduction a little bit. And so the setup is the same. You still have these log base beta of n epochs. And we still want to prove these static lower bounds for each of them so we can sum them up. And the idea is we don't want Bob to send the Bloom filter on all the memory cells of epoch J. That seems like a good idea to try not to do this. And the idea is to go back to this, move away from the communication complexity setup and go to the cell sampling idea where we sample the memory cells. So we take these two different static lower bound techniques, we just try to use the cell sampling idea instead of the communication game. All right, so just to recap what we said about the cell sampling, right? The intuition was if I had these S memory cells and I pick a random sample, okay, so I have a set of queries, assume they don't read very much from this set of cells. You can find a small sample of the cells, but there are many queries that don't read outside, right? This was the idea we had before, right? We just take each cell and include them independently with probability small enough that you'll get this number of cells. Right, so you just sample them, and then a query will survive. Yeah, it's with this probability, the sampling probability to the t, right? This is what we saw before.
So, sorry. So this is going to be for the two-dimensional range query problem again? Because you showed the sampling only for the polynomials before.
Yeah.
And it didn't work for, okay.
Yeah.
But, all right.
Okay. Right, the idea of the proof was, what, as we said, sample them at S cells, sample them with probability n over poly W times S, get the right size of the set and expectation, and the number of surviving queries is good. Right? It's just what we saw earlier, right? Each query can still be answered or reach nothing outside C with probability Q to the minus little of 1. Just the same sampling idea as before. Okay. So what we're saying here, so we have M, there's a small sample, small subset of cells where there's a bunch of queries that only read in here and nothing outside. Okay. And right, so what we did in the static low bound, right, we had this encoding proof. You took this, okay, this is a mix of slides from previous talks, so there's a little bit of recap here. And what we did this encoding proof, right, where the encoder receives some input, sends a message. If it's too small, this message, then you can recover the input. And that was the idea for the proof. So we're going to do this encoding proof again for this time for this dynamic setup. And so now we say, so here's sort of the lemma that we'll be using inside these log n different epochs, log n or log n epochs. Let me just, yeah. Yeah, so the idea is basically you receive this input, you construct the magic data structure on it, you find a small sample of cells that answer many queries, and then the encoder sends this small set of cells, and the decoder could run all the queries and get all the answers back and then recover the input, right? That was the setup from before. And the decoder runs all the queries and discards if it reads outside C. So for this range counting problem, right, you just take every single rectangle you could possibly ask, run the query, see if it probes outside the sample, and so forth. So this is what you could do. If it reads outside, discard it, and you move on. And then we recover a lot of answers, and we could recover the input. And so we're going to use this idea of sampling cells to avoid Bob sending all the cells that were red, all the green cells, right? So we want to send something smaller. Basically, we're going to sample the green cells and send a sample. So here's the lemma you can prove for range counting in 2D. You can show sort of the static thing. If the query time is small, and you have this set of memory cells M, that you don't read much from this set M, if you sample, you can find a small set of cells sufficiently smaller than N, and a lot of queries that only read in here. Right? This is just a sampling idea, right? You have a bunch of queries that only read in here, and so it's a little bit more tricky for this to get it to work for this problem because it's not the polynomial relation problem. So for range counting, not all sets of n queries will reveal the entire input. Right? That's the problem here. For polynomial relation, it was easy because all sets of n queries will tell us the polynomial. For range counting, if I have a point here and a point here and a point here, if I ask this query and this query and this query and this query, they're not going to tell me much, right? So I need something more that's problem specific, and this is sort of what I need for the range counting. So what's it saying? I have a set of cells. It's pretty small. A polylog factor is smaller than the number of points. I can find some queries where there's slightly more than the number of cells queries. So there's a polylog factor more queries. Let's say here's n is the bigger number. This is the size of C, and the size of Q is somewhere in the middle, right? So it's a polylog factor. This is a polylog factor smaller than this one, and this is a polylog factor larger than this one. Okay. So there's a bunch of queries that all read nothing outside the sample. Okay. And essentially what I'm saying here is that all the answers that you get out are independent. I'm saying that all the answers that you produce reveal one new weight each. Okay, that's what I'm trying to say here. Okay, so I can find a bunch of queries that are all reading only inside the sample, not outside, not in this bigger region, and they reveal a lot of weights if I know all their answers.
So these you're basically saying these queries, there's an actual point in your data set that's unique to each of these Q queries?
Yes, actually, what I'm...
You need more than that, but
yeah, what I'm saying, if you want the actual detail...
Like a Pareto set or something?
Yeah, if you want the actual details, it's like, so you have a fixed point set when they have weights. And now if I look at this set of Q queries, like they all reveal a linear combination over the weights, right? The answer here is it's a sum of all these things, right? This is the sum of this one. So they all reveal a linear combination, and what we can show is that this is a linearly independent set of things, and then it has full entropy. That's the argument. This is basically just because the problem is harder to prove a low bound for, a static low bound. That's the idea. You need to do something like this because not all sets of queries work. That's basically it. Okay, so there's some queries that are revealing a lot of weights. Okay, so let's try to use it on epoch J. So now we're trying to prove that you need to read a lot of these green stuff, these green cells. And what you assume is, again, right, you'll read little o of this log n over log TUW cells from epoch J. So you don't read much from these screen cells. And the encoding setup is the encoder receives all updates of all epochs, the decoder receives all of the past, and you want to encode epoch J. You want to encode the red stuff. Again, if things are independent, this message has to be at least the entropy of these updates, right? So you have to send all the updates. That's sort of the intuition, all the weights in there. So using this cell sampling idea, what we start out by doing is, so if Sj is the cells that were written in epoch J, you pick a sample of them. Right? So you pick a random sample, and by this cell sampling lemma, we can find one that's just like a polylog factor smaller than the number of updates or points in this epoch. And you can find some queries that reveal a lot of weights from this epoch. Right? That's sort of the cell sampling lemma applied to this setting, right? The static low bound. And the idea is that the encoder just sends the sample to the decoder, like we did in the static low bound. And you also send all the stuff from the future, like we did before. And so let's see if this works. So what would the decoder do? The decoder would build the data structure, like we did in the chronogram technique, all the way, or in Mihai's technique, all the way up to just before epoch J. And the decoder will start to run all the queries. And if it's in the future, we know it because it was sent in this encoding, where you have all the future cells. If it's not in the future, then we check if it is in this sample that we sent. Right? If it is, we also know the contents and we can continue. And so the last case here is, okay, if it's not in the sample, let's say someone told us it's actually in this set Q that the lemma guarantees us exists. Then so what we have here, so we know that so it's not in this sample, it's not in the future, and because these queries in Q read nothing in Sj minus the sample, they don't read in Sj minus the sample. We know it has to belong to the past, right? Okay, so that's the intuition here, right? We know if this was a query from Q and it's not in the sample and it's not in the future, then it has to be in the past. But Alice knows, right, the decoder could build the data structure up to the point just before epoch J, so she knows the contents of the cell, and she can go on. Okay, so the other case is, of course, that the query doesn't read in CJ, it doesn't read in the future, and it's not one of these queries in this set Q. And this is the case where it breaks down, right? We don't know. We're still left in this situation where we don't know if it belongs to epoch J or to the orange, to the past. And the problem is we can't recognize whether this is a query in Q or not, right? We don't know. We're just running through all the queries and we're trying to simulate it. And the problem is we still don't know whether we should sort of throw the query away or we should move on. Okay, so that's the whole idea. So we're still sort of struggling here. So it breaks down again. And so here's the final encoding. To complete the picture, the encoder also sends to the decoder what are these queries that only read in here from epoch J. So we just send this description of the queries. And so the decoding step now is build the data structure up to just before epoch J. Now you know which queries you want to run. So just start running them. And whenever it reads a cell, if it's in the future, we know the contents, right? If it's not, we check if it belongs to the sample. If it does, we know the contents. And because this is a query from Q, if it doesn't belong to the sample and doesn't belong to the future, we know it belongs to the past, and then you also have the contents, so you can run the query algorithm. So that's the whole encoding argument. Okay, so what did we achieve? So essentially, the message size, the number of bits that the encoder sends, if we make this assumption, right? So he sends the sample, right? He sends the queries to run. If there's like polynomially many queries, it takes size of Q log n bits, like there is in this 2D range counting. So only really n squared queries you care about. And then you send all the future updates, or all the cells touched in the future. And this is dominated by this set of queries, right? This is the dominating term if you set the parameters right. So basically it's telling the decoder which queries to run that cost the most in this encoding. And so the question is, how much does the decoder learn about the input? And what we said was he learns one weight per query that's being executed, right? And so essentially the last step of the proof is just if these weights have more bits than it takes to encode them, essentially we get a contradiction, right? The entropy of the output is higher than what we wrote down. So that's the last step. So here you need log n bit weights to get the lower bound, because then you can write down the queries and do this encoding step, and the encoding size is smaller than the amount of information you get back.
So you just need like twice, like 2 log, if you have n points, you need like 2 log n bits or something like that?
Yes.
Okay, so that's
yeah, and you can actually from an upper bound side make a reduction showing that you just need epsilon log n bits. You can always, in the output, that's actually enough to get the...
You don't even need to be larger than the number of points.
Yeah, you can get it to work in the other case.
And is that, you can specify Q more efficiently because, again, it's a subset of n points, so you get a n divided by Q.
Yeah, I think...
Q over n.
Yeah. I think what you can do is, for this concrete problem here, you can actually, if you want to go to epsilon log n bit weights, you can sort of split your points into 1 over epsilon copies and have one pointed with the most significant bits, one with the next and one with the next, and the query time, now you run your query on all data structures, so the query time goes up by a factor 1 over epsilon, the weights have gone down. So you can also do like an upper bound reduction. Okay. So that's basically what we got out, right? You have to read these log n over log update times the word size from each of these epochs, and we sum them all up, we get the essentially log squared lower bound out of it. So the idea is sort of like the take-home message is that we argue by this cell sampling idea that there is a small set of cells that solves many queries, and then amongst those queries you can find, because there's essentially almost n squared queries being solved if you sample, but now you find a smaller subset that all reveal, say, independent parts of the input, right? They're sort of the answers are independent, or they reveal a lot of information. And now in the encoding, you send the description of the sample cells and the updates of the future and the queries to run. And we improve because we did not have to specify. So Mihai sent all the green cells in this Bloom filter. And this we avoided this time by sampling the cells, finding a smaller subset that we could send.
So you're not using the Bloom filter at all?
No, it's gone.
So you don't even need that?
No, you don't.
Or you can't take advantage of it?
It didn't find a way to take advantage of it, at least. Yeah.
Okay.
Yeah. Maybe there's a way. And of course, the problem with this technique now is now you have to tell the decoder which queries to run. Right? That's the cost that we did not have before. And so this is basically the lower bounds that we get out. And so of course there's lots of open problems. And the current setting, as you saw, was for the static case. You get these log n over log s over n lower bounds in the best case for polynomial many queries. Dynamic case, we can go to essentially this log squared. And so I think the most promising open problem, if you want to push the techniques forward, would be the following. So what you saw here before is that for this technique to work, you need that the answer to a query has log n bits of information, right? It has to reveal more information than what it costs to write down the query. So the idea would be try to prove a log n over log n squared lower bound for the decision problem, which means that you just have to output yes or no, right? So just one bit of output. Can you prove a log n over log n squared lower bound for a decision problem? And I think that's the most promising one, even though I think I've now been trying for 4 years and I didn't make progress, but still more reasonable than many other open problems in this area. But just if you prove anything beyond log n is still the best lower bound for decision problems. So this technique here, the log squared lower bounds, I think now we have 3 concrete problems where you have such a lower bound for. It seemed that if you get it for the decision version, there will be a whole lot of other problems we can prove lower bounds for. So I think having this decision version thing would be really great. Many more problems we could close if we had this. Of course, in the long run, we want to prove something that's better than log n for the statics, and even stronger than log n over log n squared for the dynamic problems. Hopefully polynomial lower bounds, that would be the ultimate goal. One more, this is more like a concrete problem instead of pushing the techniques. This is a concrete data structure problem we want a lower bound for that doesn't seem out of reach with the current techniques. I think this is one of the most important data structure problems out there. I think even those that are not pure CS people would know what if you ever coded in a high-level programming language, you would have seen a hash set, a hash table. So it's just you can store a hash table, and these support inserts and deletes of keys, integer keys, and membership queries in expected constant time per operation. Right? It's like used everywhere, and it's part of any standard library for any programming language, and it's built into the syntax of programming language like Python and stuff. Right? So this is like a really basic problem. And so the open question is, can you actually have worst case constant update time and query time for this problem? I think this is quite a natural problem to ask, a very fundamental one. And I think most people expect that you can't, so a lower bound would be what we want. And the best current solutions that have constant query time has like n to the epsilon update time in the worst case. So there's still a huge gap. So this is the last open problem I want to mention. I think it's one of the most important open problems in the field. And now we actually went into this discussion about non-deterministic, okay, it's over here. These non-deterministic data structures. One thing to note here is that this deterministic dictionaries problem is easy if you're non-deterministic, so you need one of these techniques that works, that sort of exploits that's not non-deterministic. So there's some things you should take into consideration if you try to prove such a lower bound. That's what I wanted to say, so thanks for listening.